You know, we all dread that moment a blackout hits.
What is it? Well, it's the fundamental rhythm that makes our entire modern world, well,
But what is this rhythm, really? But why is it so incredibly hard to stop that cascade once it starts?
Which brings us to our grid's new reality.
You know, we all dread that moment a blackout hits. The sudden darkness, the eerie silence. But what if the real cause wasn't some dramatic storm or a fallen power line, but something happening silently, invisibly, across the entire system?
Believe it or not, a huge blackout often starts not with a bang, but with a tiny, almost unnoticeable flutter in the electrical heartbeat that powers our entire world. It's a story that's all about perfect timing, a really delicate balance, and what happens when that rhythm is lost.
So here's how we're going to break it down. First, we'll uncover the grid's secret heartbeat. Then we'll look at the delicate balancing act it performs every single second and how that can shatter in a terrifying domino effect. We'll dive into the battle to keep it all stable. And finally, we'll explore the tough new reality our grid is facing. Okay, so let's start with that idea. This secret heartbeat, what is it? Well, it's the fundamental rhythm that makes our entire modern world, well, possible.
But what is this rhythm, really? Is it just a cool metaphor, or is it something real that you can actually measure?
Oh, it is absolutely real. The best way to picture it is to think of the entire power grid as one single enormous machine. And at its core, you've got thousands of massive generators all spinning together in almost perfect unison, like some kind of continent-sized orchestra.
And that incredible, synchronized spinning is what actually creates our electricity. See, power isn't a steady stream like water coming out of a hose. The spinning motion creates what's called an alternating current, or AC, which naturally pulses back and forth in a steady, predictable rhythm.
And that rhythm? That's what we call grid frequency. It's simply the number of times the current switches direction every second. You can honestly think of it as the grid's pulse, its most important vital sign. If that pulse is steady, the grid is healthy. If it starts to waver, you know there's a problem.
Here in North America, that pulse is set at a very, very precise 60 Hertz. That means the current flips direction 60 times every second. In Europe and many other parts of the world, it's 50 Hertz. Literally every device you plug into the wall is designed to run on this exact rhythm. Now, you can probably guess that keeping that perfect rhythm going is not easy. And that brings us to the core challenge of the entire grid, this incredibly delicate balancing act. What makes this so unbelievably tricky is that you can't really store electricity on a massive scale, not like water in a reservoir. It has to be generated the exact instant it's being used. So that means, at any given moment, the amount of power being fed into the grid has to perfectly, and I mean perfectly, match the power being drawn out by all of us. And this right here is the crucial connection. When supply equals demand, everything's great. The generators spin at just the right speed, and the frequency stays locked in at a stable 60 Hertz. But if demand subtly outstrips supply, say on a hot day when everyone turns on their AC, the generators physically start to slow down under the strain, and the frequency drops. The opposite is also true. If there's too much supply, they speed up, and the frequency rises.
So the key takeaway is this. That frequency, that 60 Hertz pulse, isn't just some arbitrary number. It's the grid's live, real-time feedback system. By just watching the frequency, operators know instantly if the entire system is balanced or if it's heading for trouble. So what happens when that balance is lost? Well, this brings us to the most dangerous part of the whole story, the domino effect, and how one tiny little dip in frequency can spiral completely out of control. Let's walk through the anatomy of a blackout, step by step. It all starts when a major power plant or a critical transmission line suddenly goes offline. Instantly, the supply of power no longer meets demand. All the other generators still on the grid feel that strain, and they physically start to slow down. This causes the frequency to drop. If it drops too low, automated safety systems kick in. This is called load shedding. They intentionally cut power to certain areas to try and rebalance the system. But if that's not enough, and the frequency keeps falling, we get to the final critical step. Other generators start to automatically shut down to protect themselves from damage. And every single generator that trips offline just makes the problem worse, creating a catastrophic cascade that ends in a total blackout.
This under-frequency load shedding, it's really the grid's last-ditch effort to save itself. It's a painful choice, kind of like a ship's captain throwing cargo overboard in a massive storm.
It causes a local blackout for some people, sure, but the whole point is to prevent a system-wide collapse that could take days or even weeks to fix.
It sounds like a simple problem, right? Just keep things balanced. But why is it so incredibly hard to stop that cascade once it starts? Well, that brings us to the constant battle for balance.
You see, the grid has a sort of built-in defense mechanism, and it's called physical inertia. Just picture the huge, heavy turbines spinning inside a traditional power plant. They're like giant, heavy flywheels. Their sheer physical momentum helps them resist any sudden changes in speed. So when there's an unexpected power imbalance, this inertia acts like a shock absorber, buying the grid operators a few precious seconds to react before the frequency really starts to plummet.
And this timeline just shows you how incredibly fast this all happens. In the first few milliseconds, it's that physical inertia that's buffering the shock. Within seconds, automated systems like load shedding might kick in to try and help, but to actually fix the problem for good, human operators need minutes, sometimes even longer, to get other power plants up and running and restore that balance. It is a frantic race against the clock.
And that race, well, it's getting tougher and tougher every year, which brings us to our grid's new reality. You see, our grid is changing, and this whole balancing act is getting much, much harder. For starters, renewable sources like solar and wind are fantastic, but they don't have those heavy, spinning parts that give us that stabilizing inertia. Their output can also change in an instant. At the same time, on the demand side, you have things like thousands of electric vehicles all plugging in at once, creating these sudden, huge spikes in consumption. The grid is just becoming less stable and a lot more unpredictable on both sides of that scale.
And that really brings us back to the core idea. A blackout doesn't really start with a lack of power. It starts with a loss of coordination. It's what happens when that perfectly synchronized dance of thousands of machines all falls out of step.
So, if you remember one thing from all of this, let it be this. A stable power grid isn't just about having enough power, it's about perfect system-wide synchronization. The entire system is built on a rhythm, and protecting that rhythm is the real secret to keeping the lights on. If this explanation helped you understand the grid better, you'll probably enjoy the other explainers we have on this channel.